So in this question here, we see a block X and a block Y. The X is up on an inclined plane, a curved inclined plane, and it looks like it would be released and come down and hit block Y, and it looks like the two would move off in that particular direction. So there's a couple things when we look at MX that would strike us. The first of those is that we have a change in height going on. So we have a delta Z, and that means that whenever we have a change in height, that means there's gravitational potential energy. And we see that, and that's, of course, mg delta Z. And then when it gets to the bottom, we will have kinetic energy, which is 1/2 mv squared. And we see the law of conservation of energy. One will be converted into the other. Y, it looks like the initial velocity is 0. And then it looks like afterward the two collide. So we have a collision, and whenever we have collisions, we think first momentum. And secondly, we think energy for elasticity. And so in this case, it looks like a sticky collision. And so we would expect it to be inelastic, meaning the kinetic energy is not conserved. So that just looks like what's going on in the situation. And now we'll take a look at the question itself. Solid mass of X may be placed at different locations along the curved ramp. So those might be locations like here and here and here and here and here and here, like so, giving it different potential energies that it could collide. Okay, the bottom of the ramp is Y. Of mass Y, it is at rest, so we are correct about that. It was at rest on a horizontal surface. It shows that both blocks before it's released, they must graphically determine the relationship between the release height and the speed at which the two block system travels after they stick together. So we are looking at this height, delta Z, and this V afterward. So graphically, what that's going to look like then is we're going to change the height, delta Z, and to see its effect on the velocity afterward. So with different heights, and we'll know that we want it, if we're going to do this experiment, we want at least 5 because we need 5 to get a trend. All right. Shows the blocks after the collision. Frictional forces are negligible. Friction negligible. That's important for us to know. Friction negligible. All right, so state the basic principles, laws, or equations that students could use to graphically determine the relationship between the release height of X and the speed at which. So what are the principles and laws? So immediately we were talking about this here. We spoke about conservation of energy, and we spoke about momentum, which means then that we would be looking at P0 equals P. So if we're going to state those, and state usually means simply, the first principle would be the law of conservation of energy, where we have E0 equals E, and we have the gravitational potential energy will be equal to the kinetic energy. The change in gravitational potential energy The change in gravitational potential energy will be change in the kinetic energy, and that, of course, is mg delta Z equals 1/2 m delta V squared. And our other principle would be the law of conservation of momentum. P0 equals P, and that means that px will be equal to pxy. The two stick together. So those are the equations we would use. So the basic principles, laws, equations to graphically determine that relationship between those two. It just says to explain, it just says to state them. It doesn't say to explain or qualify them. But in our work here, we've already seen that that's what's going to happen. We have our potential energy becomes the kinetic energy, and that kinetic energy, or the momentum that it has at the bottom, is conserved when the two collide and stick together. So now let's take a look at the scoring guide. And so we state the conservation of energy, state the conservation of momentum. So we need to use the conservation of momentum in terms of this example response, conservation of energy, to determine the relationship between release height and block X of the speed the two-block system travels after they stick together. All right, so those are a statement of R2. You know, we could go on and say that these two laws would be necessary to determine the relationship between the height mx is released, its resulting velocity at the bottom, and the resulting velocity after the collision. And so in this case, we have included a little bit more than what they've said. We have all aspects they're looking for. It is not wrong to go into more depth, but state usually means something that's very succinct. It means just say it. It is in contrast to explanation. It does not mean explain. Now, we can explain. It's not wrong, but it's not necessary. And so that is part AI.